Okay, hello everyone. This is GS Mathematics, and this is the 9820 H3 Mathematics Introductory Lecture, Lecture 0. So, what is H3 Mathematics and why should you take it in the first place? So, we have this paragraph from SEAB in Cambridge. Mathematicians work with precise definitions, make conjectures, prove new results, solve problems, yada yada yada. I'll leave you to read this paragraph for yourself so you can pause, or we can move on and let me break this paragraph down for you. So let's dissect this paragraph. We have precise definitions, conjectures, new results, proofs. We have understanding and writing mathematical statements, proofs, and solutions. We have techniques and results. So in H3 mathematics, you are no longer bound to how repetitive the questions in H2 mathematics can get. In H2 further mathematics, if you're a student as well, the questions there will usually tend to be unconventional. So you will be given unconventional problems and you will be applying mathematical results in novel ways that you may have never seen before. So you cannot just keep doing questions and expecting the same thing to come out. There will always be novel questions that you will have to understand and break down. So it's not uncommon for questions to involve different topics, for example, a counting question on derangements involving Taylor and Maclaurin series. Derangements are concepts we will cover later. For students who have taken Olympiads like the SMO or the IMO, etc., the proof-based Olympiads, the problems in those Olympiads are less structured compared to the H3 math syllabus, and those problems in the Olympiads are much harder. So let's look at an example question. So we have to prove this inequality, we have to prove another inequality, and then we have to solve an equation. So what teachers may have told you is that they don't put these parts anyhow, they put them purposefully for a reason. So let's look at a solution. So for number 1, we invoke a known result, the Cauchy-Schwarz inequality, which we will cover in lecture 3, don't worry about that. And we need to note that when we square both sides, we reduce this inequality into this form. So Cauchy-Schwarz requires two sequences, and the sequences we will use is A1, A2 all the way to AN, and 1, 1 all the way to 1. And both sequences are of length n. So Cauchy-Schwarz allows us to do this, and the inequality is pretty obvious after you apply Cauchy-Schwarz. Now for number 2, we can just simply add up everything using this inequality. So because we have squares, we have square roots here, we can just square to get rid of these, and we will be getting this, and this is clearly equal to square root 6, and we're done. Now finally for number 3, you should notice that we have equality here, and Cauchy-Schwarz says that everything must be equal for equality to be attained here, and that means y equals to z. Sure, we have 6. Now, because y equals to z, and we have equality, x equals to y equals to z equals to 3. So therefore, x is 3. Don't believe me? Check it for yourself. Now, let's move on. What have we learned from this problem? We had to recognize existing inequalities when we had to apply to this new problem. Particularly, we had to see that we could apply Cauchy-Schwarz. We have to also use previous parts to solve the next part, as you can see over here. We had to use 1 to solve 2, and we also had to use 1 to solve 3. So we also had to cleverly spot some things, like how we spotted that x equals to 3. And H3 Mathematics will be full of these 3 steps and techniques. So if you do not like them, H3 Mathematics is not for you and you can turn this video off. Otherwise, do continue on. So what's inside H3 Mathematics in the first place? We have mathematical statements, proofs and reasoning principles, problem-solving heuristics, inequalities, calculus, and combinatorics. Essentially, 100% pure mathematics. We have, for the assessment, we have we have the one paper containing 80 marks. You need to note that this is quite a change from the previous syllabus, which had a 100-mark paper and around 8 questions. Actually, exactly 8 questions, I think. So the first 5 questions of this new syllabus are from 10 to 14 marks, and the final question is worth 16 to 20 marks. And for this final question, the new part of the syllabus is that we'll give you a piece of new math, basically a text to read, and you will answer questions based on this text as well as your existing knowledge. And this text can be pretty much on anything. For example, it can be combinatorial interpretations of harmonic series, constructions of the Weierstrass function, and also essentially proving that it is continuable, it's continuous everywhere but nowhere differentiable. And we will talk about continuity and differentiability in the later part of this lecture series. And or we can be tested on something else that we have never seen before, and it's really up to Cambridge. So what's inside the lectures? We have proof, mathematical statements, methods of proof, mathematical induction, and we have one lecture dedicated to this because there are many types of induction. We have weak induction, strong induction, forward, backward, jump induction, etc. And then we have the inequalities. We have AMGM, Cauchy-Schwarz triangle, and some more inequalities that are not tested, as in you do not need to memorize these inequalities, but doing so could be helpful for Olympiads. And you could also be tested on proving these inequalities and later using them, as we saw in the example question. We have number theory, divisibility, division algorithm, Bezo's lemma, prime numbers, etc., modular arithmetic. We have combinatorics, pigeonhole, bijection, inclusion and exclusion arrangements. We have sequences and series and recurrence relations, epsilon delta, different method of differences, APGP, first order and second order recurrence relations. There's a slight overlap with further mathematics over here, but we have chosen to include that for completeness. We also have boundedness of sequences, convergence, monotonic sequences, and the monotone convergence theorem. We have limits for functions, theorems on limits, squeeze theorem, left and right limits, L'Hopital's rule, continuity and differentiability, IVT, and the Brown fixed point theorem. And for derivatives and series, we have power series, Taylor series, ratio test, alternating series test for convergence, uniform and pointwise, local versus absolute maximum minima, Fermat's theorem, Rolle's theorem, and NVT for derivatives. For DE's differential equations, we have first order and second order differential equations, substitutions, solutions of curves, particle solutions, separation of variables, and integrating factors. There's a slight overlap with further mathematics, but we will have chosen to include it anyways for completeness. Now, we also have for integrals the final topic, reduction formulae, substitutions, integrability, mean value theorem for integrals, and relations to infinite series, as in how we can use integrals to evaluate infinite series and sums. So, what's the lecture gonna be like? So how it works is that there's going to be a grand total of 16 lectures, except this lecture 0. So we have lecture 1 to lecture 16. This is a breakdown of the lecture series, and each lecture will be accompanied with lecture notes as well as problem sets. Lecture videos like this one will be available on GSMathematics, and solutions will be uploaded to libgsn, or unless otherwise stated. So in the lectures, you will not just be taught what the content is, but we have to teach you how to apply this content and the results you learn. We will be introducing theorems, and we will also be proving those theorems unless they're too complicated. And afterwards, we will look at problems from past H3 papers as well as original questions, and we'll also be looking at math Olympiads from various math Olympiads like the SMO. So let's say you finish this lecture series. What next? The entire purpose of this lecture series is to encourage more people, not just the JC2s, to learn more about H3 mathematics. Many people think that an H3 is just really for top students. Those are our extraordinarily talented in math. However, we want to open it to more people who are passionate but don't have the resources to be able to do so. Therefore, that way we'll be able to help people train for Olympiads and appreciate the beauty of pure mathematics more. So by the end of this lecture series, you should be more motivated to learn, you should be a better problem solver, you should be able to understand everything we went through, and finally, you should be proud of yourself if you actually are able to understand everything we went through. So after you're done, what's next? You could train for Math Olympiads, you could explore math at a deeper level, do some research in those fields. You could maybe study for Math 55 at Harvard, if you make it there, and really anything that this course has taught you. So, before we begin the lecture series, here's a quote. The mathematician does not study pure mathematics because it is useful. He studies it because he delights in it, and he delights in it because it is beautiful. Indeed, that is the essence of pure mathematics compared to the applied mathematics that you would encounter usually, especially in H3 mathematics. H3 mathematics is going to put you a bit in the shoes of the university mathematician, and we are hoping that you'll stay on to continue and enjoy this lecture series. Thank you very much for watching, and have a good day.